So let's think about a spring. Let me take a frictionless surface and I'm going to attach a spring to some immovable wall. And this spring will be one that I can either stretch it or compress it. Like I can push, I have a mass attached to that spring. I can push the spring to the left. I can pull the mass to the right and stretch the spring or compress the spring. And let's use our knowledge, our empirical knowledge of the last time you jumped on a trampoline to think about what happens here. If I compress the spring, in other words, if I take this mass and I push it to the right, to the left, right, compress the spring, I would have to apply a force this way to push the spring, and that means my displacement is going to be to the left, right? I'm going to move the spring. Well, the spring, because of how springs work, applies a force right back. Which direction is it? Well, if you compress the spring, it seeks to restore this mass to its equilibrium position. So for a delta x to the left, I get a force of the spring to the right. So the force is acting opposite to the displacement. All right, let's get back on the trampoline and run another experiment. Let me now pull this mass to the right. My delta x now looks like this. Okay, what does the spring do? Well, it tries to pull it back. This is what makes trampolines fun. And so if I have a displacement to the right, I get a force, I'll do it over here, of the spring that's back to the left. Because of this nature, how the spring force is always opposed to the displacement, I call it a restorative force, right? If I move the block, the spring force tries to restore it. That means, of course, there is some position here where the block just sits still, and that makes sense. If you get off of the trampoline, or even if you lie on the trampoline and don't jump, you come to this equilibrium position. So the block has an equilibrium position, which means the spring has what we call an unstretched length. We could also say uncompressed, but it gets really obnoxious to say unstretched and uncompressed. So we just say unstretched, and we mean unstretched and uncompressed, right? It has an unstretched length, which corresponds to the equilibrium position of the block. It's just sitting still. And this is going to be a frictionless surface, I should say. Equilibrium position. Okay. So now we've got the direction down. Interestingly enough, what that direction tells us is we're going to have to introduce a negative sign into the equation we ultimately get to take into account this opposite behavior. We'll see that in a second. Now let's talk about the strength of the force, right? Let's say you're on a trampoline. So I've got 3 kids. I've got a 6-year-old, a 9-year-old, and an 11-year-old. And then there's me. So if I get on the trampoline, the thing stretches a lot. Let's just be honest about it. But if my 6-year-old gets on it, it doesn't really stretch that much. And if he jumps, he gets kind of high. But if I get on there and I jump, I get pretty high. I can get pretty high. Why is that? Because the more you compress or stretch a spring, the more force it gives back. That just makes sense. If my 6-year-old gets on the trampoline and jumps a little bit, spring stretches a little bit and it exerts a little bit of force back on him and sends him a little high. If I get on there, I stretch the springs a lot. They exert a lot more force back on me and I can get pretty high. And so it turns out to be the force is proportional. This is I should say the spring force, proportional to, we've already seen it's proportional to what we just said is that it's proportional to the displacement, delta x. What I said a while ago is it's always opposing delta x, so that invites us to include a negative sign. How is that the case? Well, if my displacement is negative, my force is positive. I get that from including a negative sign here. If delta x is negative, then the spring force turns out to be negative times a negative, positive. If the displacement is positive, this negative tells me that the spring force is now negative. So this negative symbol here takes care of this contrary nature. The displacement tells me that the force gets bigger in magnitude as I move the mass farther, if I either stretch it or compress it. So of course, the way to turn a proportionality into an equivalence is to do an experiment and come up with a proportionality constant. So let me get rid of that, give you an equal sign, and put in the proportionality constant. I'll rewrite this here. Spring force is equal to minus kx. We normally don't write the delta x because what we're going to do is insist that the equilibrium position of the spring is our origin. Usually I tell you that the coordinate system is at your disposal. In some cases it still is here, but usually the more clever way to handle this is to put your origin at the equilibrium position. In that case, x initial is always 0, and the spring for E, we can leave off the delta and just write x for the position, right? So if the position, again, if the position is negative, this gives me a positively directed force. If the position is positive, this gives me a negatively directed force. K is called the spring constant. You can imagine that that's going to be different for every spring, right? We have to run this experiment on every spring to find out the spring constant. Functions as a measure of the stiffness of the spring. If I have a really, really stiff spring, I get a really big force out of that if I move it. A really slack spring gives me a smaller force, but that's the function of the spring constant. It measures the stiffness. It's got units. I need newtons on the left-hand side here. I need meters on the, or I need newtons everywhere. Sorry, I've got newtons. I need newtons because that's all I have here. I've got meters here, which means the spring constant has units of newtons per meter. Multiply that by a meter, I get a newton, which is my spring force. Okay, this expression is called, I should write it up here. This is called Hooke's law. And this force is called the spring force. Strictly speaking, this is not true for any spring, but we're going to make all the usual assumptions we make to idealize the system. In this case, what we're going to do is ignore any internal friction of the spring, right? We did kind of that with pulleys on inclined planes. We ignored it. We said the pulley's frictionless. Well, here, the spring does not have any internal friction. What is internal friction? Well, if you ever spent any part of your childhood as a young miscreant, I certainly never, ever would have done this. But, you know, I knew people. And you take a paper clip and you bend it back and forth over and 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 over until it breaks. And then you touch it. It's hot. I never, ever would have done that in class and then reached over and touched my friend with it just to surprise them. Certainly never did that. It was a terrible thing to do. I don't even know anybody that did that, right? But if you happen to do that, or if there happened to be a young rascal in your classes in 5th grade, you might have experienced that at some point. That's internal friction. We're saying the spring, as much as you stretch it and compress it, doesn't have any internal friction. We're also going to say that we don't overextend the spring. If you've ever taken one of those springs from a ballpoint pen and stretched it, it stays stretched, right? We're not doing that. What we're saying is if we don't overextend the spring and the spring has no internal friction, it will obey this Hooke's law, where K is called the spring constant, you have a displacement x, and the force we get out of that is related to that displacement by this minus kx. This is an important system. We're going to talk about this a lot as we move forward, and for most of the rest of the class, we're going to keep referring back to this one, back to the system. So I want to introduce it to you here, and we will talk about it more and more as we go forward.